first time surpassing the performance of conventional devices. So what does that mean? What is quantum supremacy? Quantum supremacy means that you can use existing quantum computers efficiently solve classically intractable problems. So in this paper, quantum supremacy using a programmable superconducting processor by Google, they show that Google's quantum computer can solve some problem in 3 minutes, but the best supercomputer they have requires 1,000 years to solve the same problem. But by some follow-up, some papers show that actually the same problem can be solved by classical computer probably in just a few days. But 3 minutes versus a few days is still a big advantage. So now you may start wondering, what can near-term quantum computers do? Or what problems can we use near-term quantum computers to solve much faster than the classical computers? However, before we try to understand the power of near-term quantum computers, we probably need to first understand what do near-term quantum computers look like. So here is a superconducting quantum computer by IBM. And as a computer scientist, I also want to understand how to model the algorithms running on these quantum computers. And actually, most of the quantum algorithms can be modeled by quantum circuit model. So the quantum circuit model is very similar to the classical circuit model. So in the classical circuit model, you will have your input as bits, and then you will have logical gates operating on the input, and you will have multiple output bits. Okay, so you will have input as bits, logic gates operating on the input, and then bits as output. And in the quantum circuit model, you will have qubits as input. So here's a qubit, which is some quantum state. Okay, and then you will have quantum gates operating on this input, and then you will have qubits as output. But because people cannot read quantum information, so you need use measurement. So this box here to measure your quantum qubits, and then you can come up with some classical information that you can read. So you will have qubits as input, gates operating on the qubits, and then qubits as output, and then you apply measurement to extract information from the qubit. Okay, and that's all we need for the background about quantum computing today. Now we are ready to talk about the near-term quantum computer. So for near-term quantum computers, we believe that we can have more than 100 qubits soon. But the gate will be noisy, so it is not fault tolerant. So it implies that we can only have small circuit there, because like when you operate each gate on your qubit, it will give some noise, and that noise will accumulate very fast. So you can not operating on the same qubit too many times. So the circuit depth can only be small. For example, in the Google Supremacy experiment, they only have 53 qubits and only 20 layers. And the fidelity is very bad, it's only 0.2%. So it implies that 99.8% of the output is just noise. And for general quantum computers, you can imagine that we can have arbitrary many qubits, and for each gate, you only have small noise. So you can do error correction, so it is fault tolerant. So you can have arbitrary polynomial size of the circuit, arbitrary polynomial depth of the circuit. And therefore, you can do all polynomial time quantum algorithms. So here, we believe that poly and depth quantum computer, or the polynomial time quantum computer, is more powerful than the polynomial time classical computer. So, and then for the near-term quantum computers, or say the small depth quantum computer, because near-term quantum computer must be small depth here. Small depth quantum computers only has limited quantum power, so it is in poly-depth quantum computer, and it can solve some problems which cannot be solved by classical computer. But also there are some problems that classical computer can solve, but the small depth quantum computer cannot solve it. So they are incomparable. Now the next question will be, how do we use the power of a small depth quantum computer? Like here, it seems that we still have some additional power if you have small depth quantum computer. Then how do we utilize the power? And one very simple, I think, brilliant idea is to collaborate small depth quantum computer with classical computer. Like at this, you can solve all problems in green and the blue circles. And sometimes because of a collaboration, you may be able to solve more problems, like all the problems in the red circles. So how do we collaborate? One possible hybrid approach is like follows. So you have your small depth quantum computer do some calculation and send them classical information to a classical computer. And then the classical computer send information to both small depth quantum computer and the classical computer in the next iteration. And then you continue repeat this for many times, for say polynomially many times, then you can solve your problem. And actually there are many problems can be solved in this way, like factoring can be solved in this way. And also there are many proposals like simulating physics or optimization problems like QLA, BQE, and kite. So now, one very interesting question is it possible that this hybrid approach, small depth quantum computer plus classical computer, can be equivalent to general quantum computer? So if this is true, it may imply that we can have a all-powerful, very powerful quantum computer in the near future. But before answering the question, we first need to quantify how small the small depth quantum computer it is. So here, small depth quantum computer means quantum computer with circuit depth at most log n. So this implies that the circuit depth is exponentially smaller than the input size. Okay. Now the question is, can all problems that can be solved by Polian depth quantum computer be also solved by log n depth quantum computer plus classical computer? Okay. So it's like, is it possible that these two models are equivalent? And you can draw circles about this question. So the outer circles are all problems that polynomial depth quantum computer can solve. And the inner circle are all the problems that this hybrid approach, log n depth quantum computer plus classical computer can solve. And trivially, this circle is in the outer circle. And the question now is it possible that these two circles are actually equivalent? Okay, and I want to tell you some facts and conjectures about this question. So first, Richard Cliff and John Wadsworth in 2000 proved that Charles Everson only need log n depth. So it implies that you only need log n depth quantum computer plus classical computer to break crypto system. And after that, Richard Joseph in 2005 conjectured that any polynomial time quantum algorithm can be implemented with only bigger log n quantum depth interspersed with polynomial time classical computation. So it implies that log n depth quantum computer plus classical computer equivalent to Polian depth quantum computer. And after that, Scott Aronson conjectured that there exists an oracle problem such that Polian depth quantum computer is strictly more powerful than log n depth quantum computer plus classical computer. Okay, now in our paper we show that there exists an oracle problem P such that P can be solved by Polian depth quantum computer, but not log n depth quantum computer plus classical computer. So we find this problem, which is in the outer circle but not in the inner circle, in the relativized world. So relativized world means that our result is relative to some oracle. So this proves Aronson's conjecture in 2005, and also this proves Joseph's conjecture in the relativized world. Okay, I also want to mention that there's an independent work by Kodron and Amanda. They also prove this theory using different oracle problem, and their work is also accepted by Stock 2020. So now I'm going to tell you what is the problem, what the problem is. But before that, I want to give you a quick introduction about oracle problem. So actually, some problems are defined by an oracle. For example, the Simon's problem, which is a very famous problem in quantum computing. So in this problem, you are given a 2-to-1 function f, this function is from 0, 1 to the n to 0, 1 to the n, with the promise that there exists some s such that f of x equal to f of y if and only if x equal to y, x, or s. And the problem is very simple. Let's try to find s. So if you have a classical computer, then you can make polynomial queries to the function. So you can query x, and then the oracle or say the function will reply you with f of x. And you collect lots of these pairs x, f of s, and then you can try to solve the problem. And for a quantum computer, which is very similar, but the query is like follows. So you have two registers for your query. The first register will just be your question, and the second register will just be some zero, okay? And then you send these two registers to the function f, and then the function f will reply with x and the f of x, okay? So the function will put the answer in the second register. So it is the quantum query model. And how do we think about the oracle in the quantum circuit model? So we can just think the oracle as the gate, which only calls one step. So for example, in a d-depth quantum circuit, you can make at the most d sequential queries to UF. Like you only have d layers, so you can only make d sequential queries. But in each layer, you can make polynomially many parallel queries to UF. Okay. And you can just view the oracle as a gate in the circuit. So now I'm going to tell you how to design the oracle problem we have. And this oracle problem needs to satisfy two requirements. First, it needs to be easy for poly and depth quantum computer. And second, it needs to be hard for local and depth quantum computer plus classical computer. And for simplicity, we just add the quantum circuit depth to be D. Okay, and it is very hard to start from nowhere, so we just start from some problems we know. What have we known from this talk is that the Simon's problem. And Simon's problem has a very good property. It is quantumly easy and classically hard. So it satisfies 1.5 requirements. And we only need to prove the last 0.5 requirement is satisfied. Yeah. So it looks like we are almost there. However, Simon's problem is actually easy for constant depth quantum computer plus classical computer. So like here, Simon's problem is actually in the inner circle, not here. Okay. And here, because of the time limited, I cannot tell you the Simon's algorithm, but I can tell you a very crucial point about that standard approach. That crucial point is that if you can prepare polynomially many this state x, f of x, then by using some efficient classical post-processing, you can find x efficiently. Okay, and in the quantum query model, you can easily prepare x, f of x, right? Because you just view this as a gate, and then you send your query x 0 to the f, and then f will put the answers in the second register. So you will get x, f of x by just one step. So you can prepare it by one round quantum parallel queries. And this problem is easy for constant depth quantum computer plus classical computer. So this problem is not hard enough. So our idea is that, okay, this is not enough, so we try to make it hard. So we have an observation that d-depth quantum computer can only make d sequential queries. We have mentioned this a few slides ago. And then, so we try to falsify the standard approach. So we call this idea pointer tracing. The idea is that we try to disallow the d-depth quantum computer to prepare the state in d-depth by breaking the function. So what do I mean is that we first generate some random permutations f0 to fd minus 1. So there are d random permutations in 0, 1, n, and then we choose some fd such that fd of fd minus 1 of dot 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 of f0 of x is equal to f of x. So like we can visualize this construction as follows. So like you can have f0 to fd minus 1 as random permutations, and then you use some function fd to map everything back to f of x. Okay. And therefore, if you want to prepare f of x, you need to first query f0 on x, like f0 of x, and then you need to query f1, and then query f2. You need to do this sequentially. So you need depth d plus 1 queries to prepare the state x f of x. But actually, you can only use d sequential queries, so you cannot prepare this state. So it seems that standard approach doesn't work in this new construction, but we cannot rule out the possibility that there may exist a clever way to find s without x f of x. So we need more ideas. Okay, now the third idea is that we have observed from our construction that only fd and sd has information about f, right? So here, f0 to fd minus 1 are just random permutations, and only fd has the information about f. Okay. So we try to hide fd. So the idea is just try to hide fd. So we call this idea hiding. So how do we hide fd? So we just enlarge the domains of the random permutation. Right. So before that, we have permutations. We have permutations in 0, 1 to the n. Now we enlarge the domain to be permutations from 0, 1 to the d plus 2n. Okay. And the same f0 to fd minus 1 are just random permutations. For fd, if the input is in SD, so SD are like the true domain. Like here we have f0, and f0 will map s0 to s1 in the larger domain T1, right? So we have high sum domains in the larger domain, and if the input of fd is in SD, we'll map it to f of x. But if the input is not in SD, we'll just map it to both. So both is some symbol implies no information. Okay. So we enlarge the domain of Fj and let Sj be a random subset in S. Therefore, Sj is hidden in Tj, like S1 is hidden in T1 before the just round parallel occurs, like before the first round parallel occurs. So Sd is hidden before this round parallel occurs. So before we make this round parallel queries, we cannot know Sd. Therefore, Fd cannot be evaluated in D round, so F is safe in D round. Okay. Now it looks like that we must use D plus 1 sequential queries to compute Fd and Sd. So this is our problem. We call this D shuffling segments problem. And so the problem is that given F, then we use this construction. I call this construction the D shuffling oracle capital F of the function F. Okay, so you are given some segment function F, then you use a big random permutations to randomly shuffle the function, and then you will have some function fd to map everything back to F. Okay, and the problem is very simple. Given the shuffling oracle F, which is defined by f0 to fd of a random segment function F, and the problem is to find the small f, the hidden shift. Okay, and now because of time limit, I cannot tell you all the details about the proof, but it is easy to show that this problem can be solved in 2D plus 1 depth quantum computer. Okay, if it for DSSP problem, and it is hard for D depth quantum computer. So in addition to show that Paulian depth quantum computer is strictly more powerful than log-n depth quantum computer plus classical computer, we actually show a separation between 2D plus 1 depth quantum computer versus D depth quantum computer plus classical computer. And also I want to mention that actually the hybrid approach considered by Richard Josa and Scott Levinson are different. And our separation holds for both hybrid approach proposed by Richard Josa and Scott Levinson. Okay, and also because of the time limit, I didn't tell you like what exactly the models Richard Josa and Scott Levinson consider. You can check our paper for the details, or just email me. I'm very happy to answer the question. So yeah, and there are some open questions I want to mention. First, request the first I think, and this is the most important open question, is that can we request the oracle by some cryptographic assumption? Okay, like based on because oracle is the first step to prove separation. And I think the second step is that can we assume something is hard or assume some crypto assumptions, then we can separate this to composite case. Okay, and the second open question is that here we have separate 2D plus 1 and the D. And is it possible to come up with a sharper separation? For example, D versus D plus 1. Okay. And that's all. Thank you for attending the talk online. And if you have any questions, please email me or talk to me offline. I'm very happy to answer the question. Thanks.
Naihui, are you online?
Yeah, I'm here now. Yeah.
Okay. So any question? Naihui will answer the question now. Any question?
Hello. Yeah. So the separation you show is for this kind of cryptographic kind of construction. It has this flavor of cryptography. And is there some realistic problem that would have this flavor? As like any real
Okay. Yeah. That's a very good question. So currently we only have this oracle problem to separate like different depths of quantum computer plus classical computer. And the very direct answer to your question is that no, we don't have any realistic problem that can separate different depths. But on the other side, now we have the first oracle problem. And in the history of quantum computing, usually you have the oracle problem first, and then you find some good application based on the technique you have from the oracle problem. For example, we have a Simon's problem first, and then Peter Shor found that okay, there's an interesting structure in the Simon's algorithm. So he found the algorithm for Shor's problem for the factoring and proposed the Shor's algorithm. Yeah, so for this problem, we also hope we can have the same path. Like we propose some ideas in our oracle problem. Then the next step is that can we find some really useful practical problems that can separate different depths of quantum computer. Yeah.
I have a more basic question about the oracle problem, because sometimes I think when we need to do an oracle problem, the oracle itself might be defined from a classical formula or from some classical data. Is that right? So my question is, if this is the case, then may the gate containing in the oracle itself already have already requires the depth which is quite larger than your circuit.
You mean the size of the data?
Yeah, the size of the gate you need to convert your formula or data into an oracle.
Yeah, that's true. So that's why we can only view the oracle as some theoretical object that doesn't exist in practice. So if you really want to have an oracle, then yeah, like you said, for example, we consider it's a function which is 2 to the n from 2 to the n. So if you want to encode this function, you need like 2 to the n times 2 to the m times n bits. So that's way more larger than what we expect. So in the oracle model, we only expect that you are given a black box, and you don't know how does this black box where is this black box from, but you get some promise that okay, this black box is about Simon's function, and the goal is to find the hidden shift in the black box. So when you compute the time complexity of this kind of problems, you only consider like how many queries you need to query the black box and how many gates you need to compute everything after you have in the queries. Yeah.
Thanks.
No. Let's thank Nai Hui.
Thank you.